This is the Module 6 video describing the first of two palladium-catalyzed carbon-carbon bond-forming reactions. The first of these reactions continues with the theme of alkene reactivity throughout this course. This is a transformation that was independently discovered by Mitsurogi and by Heck. Heck did much more developmental work in the 1970s and 1980s, and then beginning in the 1980s, the chemical and pharmaceutical industries began exploring using the Heck reaction for producing pharmaceutical products and fine chemical products. The example that is shown here combines one equivalent of bromobenzene with one equivalent of methyl acrylate catalyzed by palladium bistriphenylphosphine diacetate using triethylamine in excess as the solvent. The major product that is formed has a new carbon-carbon bond, but retains the alkene of the product. The common name for this compound is methyl cinnamate. After 68 hours, the heat is removed, the reaction mixture cools to room temperature, and a crystalline byproduct comes out of solution in an equimolar amount to the methyl cinnamate product. Think about what the structure of the stoichiometric byproduct is under these conditions, and we'll discuss that in class. Turning to the second page of the worksheet, the mechanism for the Heck reaction was the subject of considerable debate in the decades immediately after its discovery. But workers in France, Christian Amatore and Annie Joutan, have carefully studied this mechanism, and the Amatore-Joutan mechanism is what will be presented here. The palladium bistriphenylphosphine diacetate is actually a pre-catalyst. This compound is relatively stable to air, but in solution undergoes an interesting transformation, which begins with ligand dissociation of triphenylphosphine, followed by nucleophilic addition of triphenylphosphine onto one of the acetate ligands. Some of the free triphenylphosphine then coordinates with palladium to give a structure bistriphenylphosphine palladium monoacetate anion, which is the active catalyst. There is some inefficiency in the original conditions. Due to the mechanistic work, we can think of some ways to modify the reaction conditions to make the most efficient use of palladium, since palladium is the most expensive component of the Heck reaction. We'll discuss this in class, but as a hint, the conversion of the two components of the known intermediate to these four components is not a balanced equation. On your own, also work through the electron counting to assure yourself that the oxidation state of palladium is 0 and that this is a 16 electron complex. Turning to page 3 of the worksheet, This is the proposed mechanism for the Heck reaction. This catalytic cycle begins with the palladium-0 active catalyst. L is the abbreviation for the triphenylphosphine ligand. At the very start, X is the acetate ligand. In the first step of the mechanism, bromobenzene reacts with the palladium-0 catalyst by oxidative addition to give intermediate A. Note that the two triphenylphosphine ligands, L, are trans in the trigonal bipyramidal structure. In the second step, we have a ligand dissociation. In this case, a negatively charged ligand is leaving, either acetate or bromide, and this gives a neutral intermediate, compound B. The third step is ligand association of the alkene of methyl acrylate to give intermediate C. The fourth step is 1,2 migratory insertion of the phenyl ligand onto the alkene ligand. This occurs with selectivity for the carbon ligand adding to the terminal carbon of the alkene ligand, and palladium is on the carbon adjacent to the carbonyl. Depending on the ligands on palladium, the regioselectivity in some cases is altered so that the phenyl group is closer to the ester. But under these conditions, structure D is produced. 1,2 migratory insertion is a stereospecific reaction so that the phenyl ligand and the palladium metal add onto the same face of the alkene. This is an example of syn addition, although the phenyl and palladium groups can add to either face of the alkene, but they will both add on the same face of the alkene. Step 5 is simply a sigma bond rotation to give the conformational isomer E. Conformation E is required for step 6, which is beta hydride elimination, the mechanistic reverse of 1,2 migratory insertion. Beta hydride elimination transfers a hydrogen that is cis to palladium to give a palladium hydride coordinated to a new alkene ligand, compound F. F then undergoes ligand dissociation in step 7, releasing the methyl cinnamate product, generating palladium complex G as palladium 2. It is in step 8 that triethylamine plays a role. This is an unusual type of reductive elimination in which the bromide anion stays coordinated to palladium, but triethylamine acts as a Bronsted base to remove hydrogen from intermediate G with a pair of electrons donated to a d orbital of palladium to regenerate the palladium-0 active catalyst for another catalytic cycle. Although the arrows are shown in only one direction for clarity, in fact, every one of these steps is an equilibrium reaction. At the bottom of page 3, I have filled out the table corresponding to the steps shown in the catalytic cycle above. The active catalyst is palladium in the zero oxidation state, 16 electron count. The oxidative addition increases the oxidation state by 2 to give palladium in the +2 oxidation state. Palladium remains in the +2 oxidation state for all of the steps until the reductive elimination, where palladium returns to palladium 0, and that restarts the catalytic cycle at the top. Let's also track the electron count. Oxidative addition adds 2 electron ligands to the palladium, but also removes 2 d-electrons from palladium. So the electron count increases by 2 electrons. When we lose a 2-electron ligand, electron count goes down to 16. That's required to exchange a ligand so that ligand association can occur, going back to an 18-electron complex. Migratory insertion, in which a charged plus a neutral ligand form a single 2-electron ligand that is charged, gives a 16 electron count. There's no change in oxidation state or electron count for a bond rotation. In order for beta hydride elimination to occur, which is the microscopic reverse of the 1,2 migratory insertion reaction, this step requires an empty orbital on the metal, as the formation of 2 ligands, one charged and one neutral, from a single charged ligand in intermediate E, increases the electron count by 2 electrons. Ligand association then loses a 2-electron ligand to give intermediate G. In this particular reductive elimination, only one of the ligands is lost, along with 2 electrons added to a d orbital of palladium, so the electron count remains 16. This concludes the video on the Heck reaction.